Hello everyone and welcome to RE07 channel. In today's lesson, we will explore a powerful and practical example of engineering automation using Python. As mechanical engineers, one of our key responsibilities in HVAC system design is to determine both the cooling load of a room and the electrical requirements of the air conditioning system. Traditionally, these calculations are performed manually or using spreadsheets. However, manual calculation is time-consuming, prone to human error, and difficult to repeat for multiple projects. To solve this, we will use Python to build an automated HVAC and electrical audit tool based entirely on SI units. This program asks the user for room data, calculates all major heat loads, converts the results into engineering units, and finally determines electrical current, circuit breaker size, and cable selection. By the end of this lesson, you will understand not only what the code does, but also why each step is important from an engineering perspective. Let's begin by looking at the structure of the program from top to bottom. Following the completion of your design, and after defining the exact outputs expected from your calculations, carefully craft a detailed prompt that allows the AI to generate clean, correct, and efficient Python code for your computation tool. We will utilize the case study input data table as shown in the screenshot, which includes the following parameters: room floor area, sun-facing wall area, sun-facing window area, number of occupants, lighting load, and equipment load. Think of Python like a toolbox. Standard Python is like your hands, can pick things up, move them. Import math is like opening the drawer of precision instruments, calculators, protractors, and formulas. Without import math, your code wouldn't know how to handle the complex curves of a psychrometric chart or the rounding logic required for electrical safety.
Next, we define the main function of our program, def_run_HVAC_electrical_audit_psi. A function allows us to group all HVAC and electrical calculations into a single reusable block. This makes the program organized, readable, and easy to expand later. For example, in future lessons, we could add weather API data or advanced building materials without rewriting the entire program. Immediately after defining the function, we display a header message, print, RE07, HVAC and Electrical Design Automation, SI units. This provides a professional interface and tells the user that the program operates in SI metric units. Input section, room dimensions. The first input section collects geometric data of the room, area_m2 equals float, input, room floor area, m squared. Wall_m2 equals float, input, sun-facing wall area, m squared. Window_m2 equals float, input, sun-facing window area, m squared. Here, the user enters the room floor area, the wall area exposed to the sun, and the window area exposed to the sun. We convert these values to float, because they may contain decimal numbers. These three values form the foundation of all thermal calculations. Larger surface areas mean more heat transfer into the room, and therefore higher cooling load. Input section, internal loads. Next, the program asks for internal heat sources, people equals int, input, number of people. Equip_watts equals float, input, total equipment watts, PC, TV, etc. Light_watts equals float, input, total lighting watts. Humans, electrical equipment, and lighting all generate heat inside a room. Each person contributes both sensible and latent heat. Computers, televisions, and lighting convert nearly all electrical power into heat. These values are essential to accurately estimate internal heat gain. We use int for the number of people, because people are counted as whole numbers. Equipment and lighting are entered as watts, which is already an SI unit. Thermal constants. Now we define engineering constants used in HVAC design. U_wall equals 0.45. SHGC_window equals 0.40. Solar underscore flux equals 630. Delta underscore T underscore C equals 11. These constants represent typical building conditions. U underscore wall is the overall heat transfer coefficient of an insulated wall. It tells us how much heat passes through a wall per square meter per degree of temperature difference. SHGC underscore window is the solar heat gain coefficient of the glass. It describes how much solar radiation enters through the window. Solar underscore flux represents peak sunlight intensity on a vertical surface. Delta underscore T underscore C is the temperature difference between outside and inside air. These constants allow us to calculate realistic heat gains without needing complex building simulation software. Heat gain through walls. Q underscore walls equals wall underscore M2 asterisk U underscore wall asterisk delta underscore T underscore C. This line calculates heat transfer through walls using the standard conduction formula, Q equals U times A times delta T, where U is the heat transfer coefficient. A is wall area. Delta T is temperature difference. The result is in watts, which means the amount of heat entering the room through walls every second. Heat gain through windows. Q underscore windows equals window underscore M2 asterisk SHGC underscore window asterisk solar underscore flux. This equation calculates solar heat gain through glass windows. Unlike walls, windows transmit radiant solar energy directly into the room. The SHGC factor ensures realistic estimation depending on glass type. Heat from people and internal loads. Q underscore people equals people asterisk 130. Q underscore internal equals equip underscore watts plus light underscore watts. Each person contributes approximately 130 watts of heat. Internal loads from equipment and lighting are added directly. Together, these represent all internal heat sources that must be removed by the air conditioning system. Base load approximation. Q underscore base equals area underscore M2 times 60. This adds a background load factor of 60 W per square meter. It accounts for miscellaneous heat sources such as air infiltration and minor appliances. This approximation makes the model practical for teaching and preliminary design. Total cooling load. Total underscore watts equals Q underscore walls plus Q underscore windows plus Q underscore people plus Q underscore internal plus Q underscore base, time 1.10. All heat gains are summed together. Then we multiply by 1.10, adding a 10% safety factor. Engineering design always includes a margin to handle uncertainties and real-world variations. We then convert results into more useful units. Total underscore kilowatt equals total underscore watts per 1000. Total underscore 2 equals total underscore watts time 3.412. Kilowatts are standard in electrical engineering, while BTU per hour is commonly used in air conditioner capacity ratings. This makes our program compatible with real product specifications. Electrical calculations. Now that we know how much cooling is required, we estimate electrical demand. Voltage equals 230. COP equals 3.0. Voltage represents a standard single-phase power supply. COP, or coefficient of performance, tells us how efficiently the AC converts electrical power into cooling power. Next, we calculate running current. Running underscore amps equals total underscore kilowatt divide COP, time 1000 divide voltage. This formula converts cooling load into electrical current. It is a crucial step because electrical cables and breakers must be sized based on current, not cooling capacity. Safety factors for electrical design. MCA equals running underscore amps time 1.25. Breaker underscore size equals MCA time 1.5. MCA stands for minimum circuit ampacity. Electrical codes require conductors to handle at least 125% of running current. Breakers are then sized higher to ensure safe motor startup and prevent nuisance tripping. Automatic cable selection function. Def get underscore cable underscore size underscore metric, ampacity. This function selects a standard IEC copper cable size based on the calculated ampacity. It allows the program to behave like a real engineering design assistant, automatically suggesting cable size instead of requiring manual lookup in tables.
We just built a real HVAC plus electrical design tool using mechanical engineering plus Python automation, room data to heat transfer calcs to cooling capacity to unit conversions to cable and protection sizing. Modern engineers code to save time, kill errors, and boost accuracy. Next on RE07, add live weather API data plus smarter material selection. Keep coding and practicing. See you in the next lesson. Like, subscribe, and follow RE07 channel now. Mechanical Engineer, Python Automation.